Welcome back to PV Online. And today we're going to do calculations to try to find what would be the angle of refraction given light going from one medium to another. Snell's law deals with the index of refraction and the angles. This allows us to calculate the angles of refraction. So let's do this first example, and it says a light travels from air into water. So I know we have a boundary, and let's say we're starting in air here and we're going into water. We know the index of refraction of air is 1, and we know the index of refraction of water is 1.33. So my angle of incidence is going to be with respect to the normal, as will my angle of refraction. Now I know that the angle of refraction is going to be smaller than the angle of incidence. So we were given that the angle of incidence here is 34 degrees. So using Snell's law, what I have to do is I realize my angle of incidence is 34 degrees. So I'm going to call that theta 1. That's going to make the index of refraction N1. N2 is going to be for water. That means for our purposes, the angle of refraction is going to be theta 2. The main thing is you want to pair up the angles with whatever medium they're in. So the index of refraction has to match which angle you're in. So we take N1 sine theta 1, and that's going to equal N2 sine theta 2. The index of refraction of air is 1. I've got the sine of 34. That's going to equal N2, which is 1.33, sine of theta 2. Make sure that your calculator's in degrees, and the way you do that is go up to mode and just make sure you're not in radians. So I'm going to enter 1 sine of 34. That gives me 0.559. Divide that by 1.33. Now, in order to get rid of the sine, I have to hit the second button. I want it to say in my calculator, sine to the negative first, and then put in your answer. And that gives me 24.9 degrees. So I get my angle 2 is 24.9 degrees, and that seems reasonable. My angle of incidence is 34. I know that that's going to get to be a smaller angle because I'm slowing down in that more dense medium. So for this next example, we're asked to find the index of refraction of medium B. Let's begin by making the glass N1. Now, right off the bat, do you see there's something funky with the drawing? And that is that this angle 53 is not what I want. I want the angle that is with respect to the normal. So that means my theta 1 is simply going to be the 90 minus 53, which is going to give us 37 degrees. And I have to do the same exact thing down here for B. So in this case, I'm going to make the index of refraction of B N2, which is going to make my angle of refraction 53. Now, just looking at this, can you tell, should N2 have a larger value than 1.5 or smaller? Now, look at what the light's doing. It's bending away from the normal. So that means it's going to be the less dense medium. N2 should have a smaller value. So let's use Snell's law. N1 sine theta 1 equals N2 sine theta 2. N1 had a value of 1.5. I take the sine of theta 1, which was 37. It's going to equal N2 times the sine of 53. That's going to give me a value for the index of refraction of B of 1.13. And that's what I would expect to happen. We have a phenomenon called total internal reflection. Total internal reflection occurs when the light source starts in a more dense medium. And what will eventually happen is you'll have your angle of refraction get so big that it actually ends up going parallel to the surface, and then eventually the only phenomenon that's going to occur is reflection. So we have up here, we have our flashlight, and initially when my angle is small enough, when it goes from the more dense medium to the less dense medium, the refracted ray bends away. But if I get a sufficiently large angle, I'm eventually going to get to the point to where this bigger ray just goes parallel to the surface. And we call this angle where my angle of refraction is going to be 90 degrees, We call that the critical angle. So this is called the critical angle. If I go beyond that, then the light is just going to stay within the original medium. Now you've got a really cool video showing you what's happening when light stays within the medium, and so make sure you watch it. It's just a little 2-minute, but it looks like a magic trick. But the phenomenon that's occurring is that the light is just totally internally reflecting, so no light is refracting out. All right, so in this case, I want this to be 90 degrees. So I'm going to use Snell's law, and it's going to be n1 sine theta 1 equals n2 sine theta 2. But I want that minimum angle where all of a sudden this is going to become 90 degrees, which is going to make the sine of 90 1. Well, we call that minimum angle the critical angle. So I'm just going to call that or theta c equals n2. So let's say that we initially had water, and we have water in our pool, and we have a flashlight, and we're shining it out into the air. We'll reach an angle where the light will no longer come out into the air. So let's see if we can find that. So N1 is going to be that of water, so I have 1.33, and I want to find what is that critical angle. And we're going out into air. If my angle of incidence is larger than 48.8 degrees, it's not going to come out. I'm not going to be able to see it. All right, we'll see you next time.